There we are. Hello everyone, welcome to the next episode of my science podcast. Today I'm really grateful to welcome Professor John Eiler, who is a professor at Caltech, focusing on isotope geochemistry of light elements. His research includes the origin and evolution of igneous rock, meteorites, planetary atmospheres, atmospheric and environmental chemistry, paleoclimate and paleontology. So thank you so much for joining us today.
Thank you for having me, Martha. I'm really pleased to be able to participate in your podcast.
So to begin with, please may you tell us about your career so far and what brought you to the area you're in now.
Well, I would say at every stage in my career, from when I was your age until I woke up this morning, I have never really had a specific plan as to what I would be doing the next year or 5 years later or 10 years later. I've followed my nose more, to try and develop interests in things around myself, as opposed to having some internal driver that forces me to focus on just one thing, over the arc of my career. And I would say the beginning of that, really, I wasn't so different in age from yourself. When the idea first occurred to me that I might be able to move into the sciences as an adult. And before I was maybe early high school age, the notion of what I would do for a living, honestly, it never occurred to me. I was running around out in the woods, and I just wasn't really thinking about ways of earning money and living an adult life. And then they had us take one of these sorts of standardized tests that supposedly tells you what it is you were destined to be. And it gave me two answers. It said either you should be a forester, which sounded like a very good idea to me because I liked being out in the woods and so forth, or you should be a geologist, which I thought sounded ridiculous. It's extremely specific. I wasn't good at math. I wasn't good at science. I had almost flunked out in chemistry in middle school. I'd almost been held back in fifth. Like, I just wasn't a strong student, and the idea that I would become a professional scientist seemed ludicrous. But then when I went to college a few years later, I had to pick something as a major, and I was always deeply interested in human history and the parts of human history that were sort of at the edge of what is known, the edge of what has been written about. So you might say prehistory, archaeology, anthropology. And so I thought, I'll be an anthropology major. And very quickly, I sort of soured on the idea. It was something that was a lot of fun when I was sitting at home on the couch reading books, and somehow not that fun when I was sitting in a classroom. But at the same time, I was trying to satisfy a science requirement by taking a geology course. And the professor there, a fellow named Hank Woodard, he hired me to be his porter on field excursions because I'm sort of large and I can carry things and I knew how to fish and so forth. And so he brought me on several field excursions up into southern Canada, where really I didn't do any geology at all. I just cooked and I carried his canoe around and I paddled him from here to there. But I could observe in person what being a scientist was, just the experiential immersion in people making observations of nature, people then coming back to camp and talking about what they had seen, the sort of dialectical side of people having debates and arguments and proposing ideas about things they had seen. And it really was engaging to me, just the entire lifestyle of being personally connected to nature, being inquisitive about nature, asking questions about it, debating questions about it. This really captivated me. And so I just immediately took a hard right or left, or whatever the screen is doing with my mirror image, into the earth sciences and never really looked back. It's even at that point, even as a college student, I didn't consider it a career. I wasn't really thinking about what would come the next year, the next year, the next year, until I started my undergraduate studies at Beloit College, and then I followed a person who would become my wife soon thereafter to the University of Iowa, which is where I graduated from as an undergraduate. And that was where I started experiencing the sort of feedback loop of positive reinforcement for doing something well. And I had never experienced this before, really. School. You go to school in the morning and somebody would say something nice to you about what you had done. Like, this was not part of my experience. And I started experiencing this. And I thought, why not? Like, apparently people think I'm good at this, so I'll just do this. I'll do it until they stop saying nice things to me about it. And so that was really how I started approaching the sciences as an adult, as a profession, as opposed to just being a thing that somebody assigns to you to do.
Wonderful. So we'll sort of start off you've researched the carbonate paleothermometer, and can you tell us a bit about this? So the fact that it was based on the ordering of 13 carbon and 18 oxygen in the carbonate mineral lattice. So can you tell us a bit about this?
Yeah, so first of all, it's important to understand what the stable isotopes are. So the word isotope means same place in the periodic table. So iso, same, tope, place, it's a Greek neologism. And it was invented by a social acquaintance of Frederick Soddy, who was the person who first discovered isotopes. He discovered isotopes of lead. And he realized, oh my gosh, there's more than one nuclide, more than one type of atom living at each place in the periodic table of elements. This is bizarre. The whole idea of the periodic table of elements is if you're inside one of these boxes, then everything that lives in there is an atom of a certain element, and they must all have the same properties. That's sort of a fundamental concept to learning the atomic theory of matter. And so the isotopes, they're different versions of the elements, and they differ in the number of neutrons that they have in their nucleus. So basically, what makes a thing land in a certain place in the periodic table is its number of protons, which dictates the positive charge on the nucleus. The positive charge on the nucleus, electrical charge that is, dictates how many and in what structure the electrons that surround it will be like, and it's electron clouds that really manifest chemistry. Chemistry, as we experience it, at sort of normal conditions, when I'm not in an atomic collider or the center of a star or something like that, normal kind of chemistry is all about electronic structure. And electronic structure is dictated by how many protons there are. So of course, naturally, that's what we would think atoms are. They also are neutrons, okay? And they're not electrically charged, and there can be a different number of them in atoms of the same proton number, of the same element type. And these things we refer to as isotopes. So the isotopes were really discovered in the first, gradually, over a series of observations in the first 20 or so years of the 20th century. And one of the things that people wondered about them is, what is their chemistry like? Of course, we should assume that their chemistry is mostly like each other. Okay, if I have different isotopes of carbon, well then probably they all have the same chemistry to first order. They're all like carbon. But are they different at all? Is there anything at all different about them? And this idea got caught up in the debate about the emerging theory of quantum mechanics, of the quantization of energies in light and electron motions and everything, really. And they knew that the energy contents of, say, like electrons orbiting an atom, or light that might be emitted from an atom as it undergoes an electronic transition, they knew these things were quantized, but they didn't think that the motions of nuclei in molecules as they slowly wobble and vibrate and move around, they weren't sure whether that would also be quantized. And so they approached the chemistry of isotopes with this question in mind. They were wondering, should I have a quantum mechanical understanding of the way atoms move in molecules and crystal structures, or should I think of them in a more prosaic way, like the way a baseball moves through the sky? Is it like a classical kind of motion, a Newtonian motion? And the person who really engaged with this idea deeply was somebody named Harold Urey. And he was a chemical physicist as a young scientist in, say, like the late 1920s, early 1930s. And he did a series of experiments that simultaneously accomplished multiple things. First, he discovered deuterium, which is a rare isotope of hydrogen. Hydrogen is probably the most important element to really understand its chemistry well, especially if you're made of organic matter like we are. And so medicine and all the rest of that is about organic chemistry. So that was super important, to have an isotope of hydrogen that would let you probe chemistry of organic matter. But also, the way he discovered deuterium was through the manifestation of a chemical isotope effect, a difference in the chemistry between deuterium and hydrogen atoms that arises from the quantum mechanical nature of its chemical bonds. And so this is why he got the Nobel Prize for discovering deuterium. It was why it really launched an entire discipline that I'm just one of many inheritors of. So he very quickly realized that the important thing, he realized two critical things after he discovered deuterium. One, that both led to this clumped isotope thermometer that you're referring to, this carbonate paleothermometer. One of them was a kind of chemical physics realization. He realized that what mattered in the energies of chemical bonds, their vibrational energies, is what's called the reduced mass of their motion. And the reduced mass is different. It's a little different concept from normal mass, like the mass of my cell phone. Okay, like that's an easy thing to understand. What's the reduced mass of my cell phone? Well, by itself, there isn't. It's ill-defined. But there is a reduced mass of a motion as I say, push my cell phone, okay? The cell phone has a mass, I have a mass, and the combination of the push and pull of my mass against the cell phone's mass, that's the reduced mass. Both things participate, both things that are interacting with each other have a vote on the forces and the motions that result from the forces. Also, like Newton thought of the idea of the reduced mass as a way of understanding the orbit of the moon around the Earth. He knew, okay, well, it matters how heavy the moon is, but also it matters how heavy the Earth is. Both of them have a vote on the orbital motion of the moon around the Earth. And so Urey realized the reduced mass, the motion of one atom relative to its neighbor, that's the critical thing that dictates the chemical energies and vibrations in molecules. And so this immediately led him to the idea, I'll bet it not only matters how heavy an isotope is, but how heavy its neighbor is. And that the key sort of concept about how isotopes change chemistry is most of the rare isotopes, the things that we're surprised to stumble against, like deuterium and carbon-13 and things like that, they're heavier than their normal relatives. Like carbon-13 is heavier than carbon-12 and deuterium is heavier than hydrogen. And when you take a heavy thing and put it into a molecule or into a mineral lattice, it slows the motions. And when you slow motions, you slow the frequencies of repeating motions. Planck's postulate, okay, Planck, circa 1900 or so, tells us, okay, so frequency and energy are equivalent. This is a core concept in quantum mechanics. And so if I slow something, I lower its frequency, I lower its energy, I make it more stable. So all chemical bonds in nature are hungry for heavy isotopes. They're all competing with each other. They all want the heavy isotopes, but the heavy isotopes are rare. And so they have to compete for them with each other. All chemical bonds are competing with each other energetically, trying to harvest these heavy isotopes into their bonds. And the heavy isotopes will go wherever they can do the most good energetically. They'll end up in the place where they lower the energy of the molecule the most. And Urey realized, because of this reduced mass concept, that where they really want to be is with each other, okay? Because when a heavy thing moves in relation to another heavy thing, that's the slowest motion of all. And so the isotopes not only are seeking out certain kinds of chemical bonds where they like to lower the energy there the most, they're also seeking out each other. They're sticking to each other. And this is a concept that we refer to colloquially as clumping, as isotopic clumping, that the isotopes they're rare, and so normally you'd think they might be widely distributed, but they have a tendency to seek each other out and stay each other. And so you realized this. It was one of the first ideas that appeared in his papers. So this is obviously part of the carbonate thermometer, which we'll get to in just a moment. The second part is Urey was not only a chemical physicist, he was a really important figure in the natural sciences, in the applied natural sciences like geology, geochemistry, climate, pollution, space science, moon exploration. He was kind of everywhere. He was one of the first real polymaths in the chemistry of natural materials. And so he also, at about the same time, proposed the concept of a paleothermometer to reconstruct the climate history of the Earth in the deep past. And it was a really revolutionary concept. And it came at a time when people kind of understood the age, they knew the age of the Earth loosely. They knew it was very old. They knew that the ice ages had happened, but there were a lot of basic questions about, were the ice ages rhythmic or were they irregular? Was it really cold everywhere? Or was it only cold where there was ice? There were all these questions that now we feel like we understand, but at that time really were open ideas. And so Urey knew that if we had a way to quantitatively reconstruct the temperature at certain places and times in Earth history by interrogating the properties of minerals that were deposited then, this would just be revolutionary. And so he proposed the first tool that led to the discipline of stable isotope geochemistry, which is the study of the chemistry of how isotopes get distributed in nature. And his tool was based on the concept that the rare isotope of oxygen, oxygen 18, in the ocean has to make a decision whenever a mineral is grown. Okay, whenever a coral grows or a mollusk or something grows a shell of calcium carbonate, it incorporates oxygen atoms into the carbonate mineral lattice. And when it does this, the oxygen 18 that's in the water has to decide, would I rather be in this mineral or would I rather stay in the water, or do I not care? And the energetic decision it's making is based on two things. It ends up being important that there are these two things. One is this vibrational energy term that I've been talking about. Where of course, it would like to be in the place where it slows frequencies of motion the most. And for that reason, it would like to go into the carbonate minerals, into the corals and the mollusks and other skeletal materials. On the other hand, there's another energy term in chemistry called entropy. And one part of entropy is randomness, okay, homogeneity or randomness in distribution. And more random systems have higher entropies, and more high entropy systems, they're more favored the higher temperature gets. That sort of makes intuitive sense. If I had a plate full of ping pong balls and I started shaking it a little bit, well then I might be able to keep them all in a certain part of the plate. But if I start shaking it like crazy, well then they're going to go everywhere. Okay, it's a similar kind of concept that the rare isotopes, they kind of want to go everywhere if the temperature gets high and all atomic motions are fast. And Urey realized there's this tension between the vibrational energy, the quantum mechanical energies of chemistry saying, pull the heavy isotopes into the minerals as they grow. And then entropy has a contrary vote. It says, no, I want them to be kind of everywhere. I want them to be randomly distributed. And there's this dynamic tension that then has a different consequence at different temperatures. When it's hot, entropy is winning, and you see random sharing of the rare isotopes between the ocean and the minerals. At low temperature, the vibrational energy term wins, and you concentrate the heavy isotopes into the minerals. Beautiful. This is something that carbonate is widely distributed in the geological record. We have carbonate minerals that are billions of years old. We have carbonate minerals that are distributed all over the Earth. We can now use this concept of isotopic separation or partitioning between water and a growing mineral to determine the temperature of the Earth's surface through time by seeing how strongly was it separated.
Amazing.
Brilliant, yeah. So this then led to hundreds of people's careers, numerous people in the National Academy and the Royal Society and all these places. Their careers were just about this concept, about this tool. The problem is we have lots of carbonate minerals in the geological record, lots of fossil carbonates. Where are my fossil oceans? Okay, I don't I don't get to see the water that the mineral grew from. And so if what I care about is the separation of isotopes between the water and the growing mineral, I have to see them both. So I see how strongly they got separated. If I only see one, this isn't a thermometer. This is half of a thermometer. It's like if somebody handed you a thermometer and they said, oh, wait a minute, and they cut off the bottom where all the mercury is. Here, now use it. Okay, it doesn't work. You have to have both ends for the thermometer for it to work. So people talked their way around this problem for decades. They basically said, well, what if I guess what the ocean was like? Okay, now you're just guessing what the temperature was like. Or what if I assume something about the ocean? Congratulations, you just assumed what the temperature was like. But they couldn't really solve it, not in a generic way. And so what I did to create this, I know this is a shaggy dog story, but along the way you're learning hopefully a lot of different related things. What I did is I took these two halves of Urey's idea and I combined them. I said, there is also this preference of the rare isotopes to find each other within a single material. And that also is temperature dependent. At low temperature, they really want to stick to each other. And at higher temperature, they'd rather be randomly distributed through a structure. And I just invented a sort of technological way of observing the extent to which the heavy isotopes were sticking to each other in the carbonate mineral lattice. And they do it a lot when they're cold and not so much when they're hot. And this then is a way of doing Urey's thermometer, Harold Urey's thermometer, on the same material with the same breadth of application, but you don't have to know about the ocean. You no longer care about the ocean. So that's that whole idea.
So does this have implications for the future because of climate change and warming oceans? So that it's going to favor the latter more. So is that going to have an implication for the future?
For sure. So one of the major applications of paleoclimate research is predicting future climate, which is intrinsically, it's tricky in a lot of different ways. So one of the reasons why it's tricky is that the Earth is just a big, complicated system. So how do you even describe what the average of the Earth is doing, and how does the change in the average temperature of the Earth even, what does that even mean to me? Like, I don't experience the average temperature of the Earth. I experience the temperature where I live and from day to day and so forth. So how do I relate these things to each other? So that's one problem. Another problem is that the Earth doesn't have a single thermostat dial. Okay, it's not like going up into your house and you're like, well, I want it to be warmer. So if I take this one button and I push it, it'll get warmer. That's an engineered system that overcomes all of the ambient influences on the temperature in your house. How sunny is it on the roof, and how reflective are your windows, and did you close the curtains or not, and is there a crack under your door? All these things matter. You overwhelm them with an engineered system, and you just push it until it becomes whatever temperature you want it to be. Well, nothing is pushing the Earth. It's just responding to all of these different influences that it has built into it. And so how are you supposed to predict how a system evolves when it has multiple interacting parts? And you can try and do it as an exercise of pure thought. And this is what the modeling activities are like. The modeling activities say, and we've been doing this for many, many years. Gustav Arrhenius, who's a very famous chemist who came up with the Arrhenius diagram, if you ever learned about energetics of chemical reactions. In the late 1800s, he was writing about the greenhouse effect and how the Earth could warm if CO2 came into the atmosphere and so forth. He knew about the first order effects. He even got the direction and the order of magnitude right. All of these things, albedo or reflectivity, CO2 in the atmosphere, clouds, people have known about this stuff for 150 years. But how do you put it together? How does one influence the other? How do they feed off of each other? This, you have to have a lot of detailed understanding to describe it well. And you can only come up with that detailed understanding through a kind of iterative process of recognizing the fundamental mechanisms like the greenhouse effect or like albedo, and then going and studying places and times in Earth history where they've operated in different combinations. And so probably the most important societal impact of paleoclimate research is it lets us use all of Earth history as our laboratory. And we get to control the experiments because the Earth did whatever it did. But over 4.5 billion years, it did a lot of different things. The Earth has frozen over. The Earth has been incredibly hot. The Earth has oscillated back and forth between them. It's had steep temperature gradients from the equator to the pole. It's had shallow gradients. It's had continents at one end. It's had the continents at the other end. It's been cloudy, less cloudy. It's been so many different things that if we can just reconstruct all of the different states that it has had, those will be independent. It's sort of like somebody did, like we want to do laboratory experiments to understand how the climate works, but we can't. But somebody else did. They did a whole bunch of laboratory experiments, but they didn't keep very good books. Okay, and we wander into the laboratory after their experiments and we're trying to figure out what in the world did they do and what did they observe. We're trying to piece it together from this. It's like they took their lab books and shredded them and threw them in the air or something. And we're piecing them back together. And so this is really what paleotemperature reconstruction is about, is learning how it has its own motivations as well. So some people are doing it to predict what climate will be like in the future. I would say that's the most important thing you could be doing. But it's okay to be interested in other things as well. Some people just really think it's cool to think about deep Earth time and what was the Earth like back then, and so forth. So that's perfectly valid as well. But so this is the connection to climate change.
Absolutely. So you talked about earlier this clumped isotope analysis. So you did this on eggshells to determine the body temperatures of two different types of dinosaurs during the late Cretaceous, I think. And you determined the body temperatures during periods of ovulation. So how did they differ in thermophysiology?
Yeah, so this was really a great deal of fun. This is something that was a series of projects really that were led by a scientist named Rob Eagle, who's now at UCLA, and a whole bunch of other colleagues of ours at the Natural History Museum in Los Angeles and a few other places. And we looked at both eggshells and at bones and teeth as well, because your bones and teeth, they're made of phosphate, calcium phosphate, but they have carbonate in them as a trace substituent. And so the eggshells, they're calcium carbonate. The teeth have a trace of carbonate. You can use the concept of isotopic clumping in the carbonate mineral structural group of minerals in either one of them. And he did both. And so the question we were trying to address here boils down to really one of the central debates about what the dinosaurs were like. Okay, we know they were big. That's sort of obvious. We know they were vertebrates because we have their bones and so forth. We can place them phylogenetically somewhere between things like reptiles and things like mammals and birds. But if you haven't really seen one living and walked up and touched it and watched what it did and watched how it moved around and watched what it was eating, you have lots of questions about how they really lived their lives and what they were really like. Just seeing the skeleton alone, it only answers so many questions. So one of the debates about different possible interpretations of how dinosaurs worked concerns their metabolic physiology. And at one extreme, they might have been warm-blooded like us, meaning that their cellular machinery operates much more quickly than it needs to. So they're burning energy constantly to keep body temperature elevated in order to support a high level of activity. So basically the fact that I can get up in the middle of the night in the winter and go running if I wanted to, that's an amazing thing, but it comes at a cost. Okay, I have to eat a lot of food to be able to have a body that is capable of that can just, on the turn of a dime, I can be active and sustain that activity. It's because that I'm maintaining my body temperature and all the metabolites that are needed to do that are being maintained all the time. The other extreme, you let the environment dictate your body temperature. you save enormously in the amount of food that you require to operate. So like a songbird and a good-sized garden lizard, they're very similar in body weight. The songbird eats as much in a day or two as the lizard does in a whole month.
Mm.
So that's an enormous difference in terms of your demands on making a living in the environment. But then that comes at a cost as well, and that you're not so active. And if there's a well-fed mammal around, they are going to eat your lunch, and maybe you. So it's a sort of a dynamic tension here. Which one is better? It's hard to say. This is why both exist. Is in different times and places, different approaches have different advantages. So this is the extreme: cold-blooded, warm-blooded, fast metabolism, slow metabolism. But there are other possibilities as well. So there's something, there are organisms that oscillate between fast and warm-blooded metabolisms. If you were anesthetized for multiple hours, your body temperature would drift. You would lose the ability to regulate your own metabolism. So even our own warm-bloodedness, we think of it as intrinsic. It's kind of a fragile thing. It could go away. If certain things are done to your neurophysiology, it'll stop working right. So there's different approaches. They could even have different metabolic strategies at different stages of life. Like maybe they're warm-blooded when they're young and they're cold-blooded when they're old, or the opposite. All these things are possible. A very popular version of this is something called gigantothermy. And gigantothermy says your body recognizes the advantage of being warm. Okay, so your enzymes operate at some optimal rate at certain temperatures and so forth. That's all good and will let you be relatively vigorous, but you don't want to pay the cost. You want to be warm for free. And one way to be warm for free is to get really big, because you dissipate heat to the environment or exchange heat with the environment as a function of your surface area, but you generate heat metabolically as a function of your volume. And your surface area to volume ratio drops the bigger you get, assuming you have some normal shape. So, one thought about why dinosaurs were so big is this was their way of, maybe it accomplished several tasks. Maybe it was harder to eat them if they're really big and so forth. But the core thought was maybe they were so big because this was their way of being warm without having to pay the cost. They paid a cost, I suppose, in growing. But they didn't have to pay a daily cost in maintaining all of that metabolically. So how do you tell these three apart? These three ideas: warm-blooded, cold-blooded, gigantothermy. You have to know body temperature as a function of size. If you see everything is warm irrespective of size, like songbirds and whales, they're basically the same body temperature. Okay, maybe a couple degrees different, but it's not very big difference. If you're instead a lizard, like a crocodile, is really quite a bit warmer than a similar body plan tiny lizard living in the same environment. The tiny lizard is totally following air temperature like all the time. Maybe it's basking, lying in the sun for a little while every day, but it's spending almost all of its time at the air temperature. The crocodiles, alligators, they're actually elevated a few degrees above air temperature because they're just big enough that the gigantothermy effect is starting to kick in. But both of them will be colder than the optimal that a warm-blooded animal will maintain. And so this is what we did, is we went out and tried to reconstruct the body temperatures of big and little dinosaurs. And we also considered a few different basic body plans, things that were bird-like, things that were more stumpy, like a brontosaurus. I know I'm not supposed to say. Maybe no. Now you're allowed. See the whole brontosaurus thing. Like is brontosaurus a scientific word? Well, I'm a scientist, but I never stopped using it because it's what they taught me when I was like 5, and I refused to stop. And sure enough, they came back around, and now I'm allowed to say it again. So that's being obstinate has its advantages. Anyway, our basic finding is that the smaller dinosaurs, things that had body weights less than, say, 100 kilograms, they were close to environmental temperatures. So they had body temperatures that would be, almost 10 degrees centigrade in some cases, lower than our body temperatures, and not so different from Cretaceous climatic temperatures. Whereas the big ones had body temperatures similar to our own. And the really big ones, the titanosaurs, the evidence is a bit sketchy, but what we've seen says they were even a little warmer than we are. So that a titanosaur would have a core body temperature not so different from like the highest Earth's, 40, 41 degrees centigrade, something like that. So this suggests that overall, you could have special unique explanations for each one of them because these are different species. But if you were trying to impose an overall interpretation to all the dinosaurs, you'd say they were basically following gigantothermy, that they were not metabolically warm-blooded like we are. They were sort of body plan warm-blooded. They stayed warm just by being really big. And the ones that weren't big were not warm.
Okay. So for my next question, we'll move on quite largely, but what are the possible consequences of anthropogenic emissions of hydrogen? And this might be associated with the transition to a hydrogen economy. So what did your research show on the hydrogen budget and about what I've just explained?
Yeah, this was one of the most interesting experiences that I had as a scientist. So I'm not an atmospheric chemist by long-term profession anyway. It's something that I sort of have dipped into and out of at several different times in my career. In this particular case, I sort of wandered into this problem by bumping up against colleagues who were interested in it. And the first colleague I bumped into was a scientist named Jared Ledbetter, who's a geobiologist. He basically studies the biology of natural environments, especially microbial environments. And I ran into him in the hallway, and like you often will do with a colleague, I asked him, well, what are you interested in today? What are you thinking about? And he says, well, I'm thinking about the gas that comes out of the back end of a termite. And I thought, well, that's weird. What is it? It's molecular hydrogen, H2. I said, well, that must be strange. I mean, there isn't really any in the environment, but the Earth's atmosphere is oxidized. So hydrogen is one of the most reduced things that there can be chemically, and oxygen is one of the most oxidized things. So they can't coexist with each other, right? He said, no, stupid. There's lots of hydrogen in the atmosphere. And he's perfectly right. There's a lot of molecular hydrogen in the Earth's atmosphere. It's the second most abundant reduced gas in the atmosphere. And it's produced both by things like termites farting. Okay, sometimes it's cows and sometimes it's for termites, but basically lots of large-bodied animals maintain microbial communities in their guts that ferment organic matter, and they generate molecular hydrogen as a product, and then it escapes from them. So that's actually surprisingly big source. And then in addition, some of it gets made in the atmosphere by light-driven chemistry, photochemistry, breaking down methane and other organic matter. So I thought, well, that's weird. And I wonder who has done anything on the isotope chemistry of all these processes, because hydrogen and its rare isotope deuterium, they're so different from each other in mass. They're a factor of 2 different in mass. So any time when isotope mass influences chemistry, the hydrogen isotope effects are the biggest of all. And I thought, if lots of people have done this, it would be interesting to read about. If nobody has done it, well, then we should go do something and get involved and try and lay down some initial studies. And a few people had peeked at it, but there wasn't really very much work that had been done. So, so my group did a few papers about this, and we focused on the environmental chemistry of hydrogen, because I was aware that it was also a technological issue, that people were thinking of it as an alternative fuel to use in place of fossil fuel combustion, to use them in fuel cells to basically generate electricity by oxidizing molecular hydrogen to water over catalysts. And so if you were to do this at a big enough scale, that would actually matter. If it's a little tinker toy experiment that you do for fun, well, then it doesn't matter. But if you convert all of the fossil fuel combustion energy generation to fuel cells using molecular hydrogen, well, then this is, multiplied by 7 billion people. This is a huge activity. And I was a little surprised how little had been said about the environmental implications of this, because molecular hydrogen, it's not toxic really in low concentrations. You breathe it and so forth, and it's not a greenhouse gas in any meaningful way. but it is very reactive in the atmosphere. And so it gets involved directly and indirectly in the photochemistry of lots of different trace constituents of air. I've already mentioned that it's produced by the breakdown of methane, but then the hydrogen that gets produced, it goes on to react with other oxidized species, highly reactive oxygen atoms and so forth in air. And so it acts as a sink to draw down the concentrations of things that, if left alone, would go on to react with other things. And so it has a kind of knock-on effect to the chemistry in the atmosphere. And one of the potential influences that it has is in changing the concentration of ozone in the atmosphere. That basically, if you really elevated the concentration of H2 in the upper atmosphere, it would act not aggressively like the chlorofluorocarbons, but it would have some influence on the concentration of ozone in air. And it would do it through a couple of different mechanisms. The main one was in moistening the upper atmosphere, that basically it's a way of delivering hydrogen atoms to the upper atmosphere, which then get oxidized to water. It's cold up there, and so the water condenses to make ice, and it's the ice grains that are then the sites of ozone destruction. So, whether or not this would happen to a substantial degree, who knows? It's not happening now to a great degree, but then again, we're not pumping out tons of molecular hydrogen right now. So I thought that would be an interesting thing to work on. But it has two halves, one half of which I can really speak to, and the other half of which other sorts of scientists need to speak to. The half that I can do something to contribute to has to do with understanding the budget of molecular hydrogen. What are its sources? What are its sinks? What is its fate? How is its concentration likely to change as a result of changes in its budget? If I add a new source, how much will the concentration change? And so that's my group worked on components of that. Other groups were working on similar sorts of things. The other side is, what are the consequences? If I raise the concentration of molecular hydrogen in air, what will happen? And this is one for the modelers to do, because this is something that hasn't happened to the best of our knowledge. No time in the recent geological past, no time that we can reconstruct has this occurred. And so you have to guess in a way, like it's not an uneducated guess. You use quantitative models that know about chemistry and mixing in the atmosphere and so forth, but you have to sort of guess. And so for this, I worked with a colleague, Yuk Young, who is an atmospheric modeler. He studies atmospheric chemistry and draws together all the things that we know about atmospheric chemistry and combines them into big integrated models. And so he made a prediction. I made a statement to him, well, if we generate a huge amount of molecular hydrogen to drive our economy, and if it leaks to the atmosphere in the way that other things we handle leak, like natural gas, then this is what the concentration would be like in air. And then he said, oh, okay, well, if the concentration's like that in air, then this would be the consequence. You would draw down ozone some nominal amount, 10 or 20 or 30%, something like that. And that was really all we said. And to me, it was interesting because it was a rare instance, maybe a singular instance in my experience anyway, of somebody actually going through that whole chain of reasoning before you had a problem, okay? And so to me, that was the importance, is that we said, not do this, don't do this, but here is some consequences of one path of action, and let's think about it before we do it, instead of what we've done for CO2 and lead and everything else, where we'd like do it for centuries and then go, oh no, what have I been doing? So that was sort of the idea. But anytime you get involved in a scientific question that has commercial implications, has political implications, financial implications, the economy, the energy economy of humanity is one of the biggest problems that you can possibly get enmeshed with. And so there were dramatic reactions, like lots of people got mad about these few papers that we wrote. I thought unreasonably, but they have their own perspectives on these things. And some of the anger, I would say, came from a place of interest, okay, of people who were interested in defending a position that they were very invested in, about maybe it was a financial investment in a technology or a research investment in technology. They wanted that technology to advance and felt that its upsides were more important than any downsides. And so you should attack anything that points out downsides. That was sort of one line of reasoning. They thought we did it wrong, okay, that there were things in our parameterizations that were wrong. And that, I would say, is a very reasonable critique. But anyway, it was an interesting experience. I would say that the major point of contention, the one that's most important, is the question of whether, if we do this, if we have a hydrogen economy, will we leak hydrogen to the atmosphere or not? And if you have a kind of ideal, if you have a tank half full view of the future, you would say, well, we don't want it to leak. You know, it's worth money. Why would it leak? We'll use it. We'll use it with perfect efficiency. And so of course it won't leak. And if they're right, then perfect. Then there's no environmental consequence of a thing that never leaks. The other perspective would be to say, well, how about things that we use now that are kind of like hydrogen, like natural gas? Do they leak? We don't want natural gas to leak, does it? Yes, it leaks everywhere. It leaks constantly. And it doesn't leak in the laboratory where you take your perfectly engineered pipe fittings and put them in a hood and measure around them and see that they're leak tight, but they leak in reality because human beings are not good at assembling and maintaining things, and they don't care, and welds get made badly and pipes break, and that just leaks. So this was really the major debate was, do you think humans will do this well, or will do it in a shoddy manner? And I don't really have an opinion. We'll see. The point of our work was to point out the issue and say, if you do this badly, there will be a consequence. And maybe you look at that consequence and say, that's not so bad. I'd rather do it than not do it. Or maybe you try and engineer around it so there aren't any leaks or something. Anyway, it was a way to put the issue on the table.
Absolutely. And so to finish off, we'll talk about some of your work on meteorites. So how do aqueous altered meteorites provide insight into the origins and geochemical cycles of water on bodies other than Earth?
So there's a couple of different reasons to study this problem. One of them is, most of the objects that are orbiting the sun are small. They're asteroids. And understanding their composition, their history, what they've been through is just intrinsically interesting. Anybody who studies the natural sciences should be intrinsically interested in something that is abundant and exotic. There's a second reason to be interested in this, though, is that the aqueous chemistry of the interiors of asteroids is one of the environments where something called prebiotic chemistry can potentially take place. And this is increasingly important in my research program. I would say most of the people working closely with me in my group right now, they're interested in different sides of the problem of prebiotic chemistry and its comparison and contrast with biochemistry, the products of biochemistry. And so the reason why it's such an important environment of prebiotic chemistry is that it brings together primordial materials that we know are very reactive and capable, at least in the laboratory, of supporting chemical reactions that will generate an incredible array of biologically useful molecules like the amino acids and sugars and things like that. And so if we're going to ever have an understanding of the origin of life on the Earth and the potential for the origin of life on other planets, we need to know how this chemistry works, and we need to reconstruct it in detail. We know that it's productive. When we take these meteorites and grind them up and dissolve their constituents, we see a lot of organic matter. And so you could just be satisfied with that and say, like, well, I guess somehow it happened, so I'll assume it could happen other places. But a better approach would be really deconstruct how that happened. so that if you know the elementary steps that were involved in that chemistry, now you have a basis for predicting whether it could have also occurred on the early Earth, once you understand its conditions. That then loops us back to climate reconstruction, or the interior of Enceladus or another outer solar system moon, where we see it's like an icy body. It's kind of almost as big as a planet, and yet its chemistry and materials are more like the asteroids. So maybe life could exist there, or maybe prebiotic chemistry is very productive there. In order to answer these questions, we have to understand mechanistically how the prebiotic chemistry works. And the meteorites, that comes from asteroids, these are a sort of natural laboratory that let us do this. So answering this question requires that you be able to take a collection of molecules and sort of sort them into a genealogy, if you will, to reconstruct the reaction network that shows you, oh, this molecule begat that one, begat that one, begat that one, in the following sequence and by the following mechanisms. And doing that after the fact is extremely tricky. You just have a big collection of things. You don't know which one came first and which one came second and exactly how the atoms rearranged to do it. You can speculate about how it could have happened and try and recreate those reactions in your laboratory, but that's not the same thing as knowing how it actually did happen in a specific sample. And so the role of my group in this field is to use the chemistry of isotopes in complex organic structures, where we're again doing like clumping measurements and measurements of how isotopes are distributed between non-equivalent molecular sites in molecules, to try and create a kind of map of how each molecule then led to its neighbor.
Wonderful. So do you have anything we haven't touched on that you'd like to talk about, or something about your most recent work?
I'm afraid I don't have time to go into too much more, but I've really enjoyed talking with you, and I hope that we covered enough different subjects to be of use for your podcast.
Absolutely. No, it was wonderful. It was really, really wonderful. So thank you so much for your time.
Yeah, well, thank you again for reaching out to me and inviting me to talk.
Thank you, and thank you everyone for listening.